Once again, welcome to our General Interest Seminar. I'm Isaac. I'm an HPTC of Sharcnet based at York University. Today I'm going to present best practice in Graham. This seminar targeted on the newbies who actually never used the Graham systems before or rarely used the Graham systems. So in this seminar, I'll briefly go over some overview of Graham system. So I'm going to introduce what will be the hardware side of resources. And I'll explain how to use module and managing files. And eventually, I'm going to show you some demonstration how to submit your job in our Graham systems. So here is overview. Graham is one of the latest system in Compute Canada hosted by Sharcnet at University of Waterloo. Graham has more than 30,000 CPU cores and more than 300 GPU cores. As you see in this kind of picture of left side, we have large big rooms accommodating many racks of the physical nodes under University of Waterloo building. So those machines connected using the interconnector with 100 GB FDR InfiniBand interconnection, and also there is a 56 GB InfiniBand interconnection as well for GPU's code. And CPU node, we have 800 nodes. Each node has 32 cores per node. So each physical node has 32 cores, and some of machines has more memory on the physical node, which has 256 GB large. We have 56 nodes about it, and each node has 32 cores per node as well. As you see here, even though we named the Graham as a single name of the system, each physical node has a slightly different hardware configurations. So sometimes you want to run your job with a large scale of memory. You need to specify some node information as well. Furthermore, Graham has GPU nodes as well. So if you target to run your NVIDIA code or GPU code, you can definitely submit your job to our GPU nodes. Graham is named in honor of Professor Wesley Graham, the first director of the University of Waterloo Computing Center. It has almost 3 petaflops of peak theoretical computation performance, which is less than top 50 in top 500 supercomputer list 2 years ago. And total memory is almost 150 terabyte memory. And as you briefly see in the picture of the right side, we have water cooling kind of system over the racks. So computing node will be cooled down using the water, which is actually very effective, a very efficient way to cool down the system. And also Graham has a big data ready. So we have 5 petabyte parallel storage systems. And also we offer cloud computing stack using OpenStack. This is brief information about the CPU information. We have Intel Xeon chipset on the CPU node. We have NVIDIA P100 Pascal GPU node. And as I mentioned, we do have some storage. And we're going to go over file systems later. We have a home directory, scratch directory, project directory. So each directory has a slightly different purpose. And most likely for everyday practice, you may want to use Scratch or Project, and you may want to save your file or back up your file in your home directory. Once again, I'll go over some file system overview at the end of this seminar. Okay, now let's get to the real practice, especially for module first. Module, or some people call this one as L mode, module is actually is configuration file for your software environment. Long time ago, when you need to use Intel compiler or Python or Purview, you have to set all the paths for the library. You have to set all the paths for the include the files. However, in the module systems, you don't need to specify individual packages to set up. By simply loading each modules onto your working environment, you can easily access to those kind of software packages and use it easily. So for example, as you may see here, we have a hardware operating system and shell. Shell is the login mode of the Graham. And by loading individual modules one by one, Intel compiler, Python, and Purview, now you can have your working environment. Here is just one screenshot of module list. If you log into the Graham system, you can definitely see this module list as a default. So as you see here, from 1 to 8, each modules automatically loaded when you log on to Graham system. There are a couple of things you may want to take a look at carefully. So firstly, each module has some version names. So for example, for number 6, Intel compiler. Intel compiler has a version 2016.4. As you may know, Intel compiler has multiple different versions. So we're going to see this soon though. Intel compiler must be specified when you load or unload, like with the version name as well. And OpenMPI, standard environment, everything actually loaded as a default. And here are some explanation about tag. S means module is sticky. Sticky means actually permanent. We're going to learn about the module purge command. Even though you try to purge all the modules, these sticky labeled modules are not going to unload it. So sticky means permanent. And M means MPI implementation, which means you need this one for the MPI or message passing interface programming. And some packages actually named as a math or tagged as a math. And T means for tools, which means for the development. And H is a hidden modules, which is related with another modules. It's a dependency existing. When you use module, you have to know how to find your targeted module or how to find the module you need. So there are two different options for search. So search for modules is with the module spider command, generally speaking. This command searches the entire list of possible modules. The difference between module available or avail and module spider is module avail may not list modules that are incompatible with the existing modules. So here is a short demonstration, you can see that. So I typed module avail, and then it will show you all available modules, which is really long. So I clear the screen, and I typed module avail looking for GCC compiler. And then module system reply back to you. There are a couple of options. And you can try to find some information using module spider as well. Module spider will give you full details of each modules. You can see that. It's a little bit different from module avail. And module spider and GCC will give you a little bit different format of return, like this. Sometimes you need to change your modules. As I mentioned, there could be a couple of default modules loaded when you log on to the Graham system. But sometimes you want to change your module from Intel compiler to the GCC compiler, and sometimes coming back. So you can definitely load your module using module load and module name. Module name can be found using module avail or module spider, and you can unload your targeted module from your list of modules. And sometimes you want to unload all the modules you actually loaded except the sticky ones. So here is a short demonstration. So module list I'm checking out. And then I want to unload this Intel compiler. So module unload Intel and version name. So as you see, inactive modules. So when you check it out the list one more time, you can definitely see Intel modules already gone. And then I want to check what type of GCC compiler is available. And I want to load some default GCC compiler 5.4.0. So I'm going to load module load GCC 5.4.0. And then you can definitely see now I have a GCC compiler in our module list. And also when I change my GCC compiler, OpenMPI package automatically changed. I'll explain about module hierarchy later on a little bit more. So as I pointed out, when I have Intel compiler, the OpenMPI actually connected with ICC compiler, which means when you have an Intel compiler, you should have OpenMPI related with Intel compiler. Otherwise, it's not going to work properly. When you do the module load GCC, that will automatically replace Intel compiler with a GCC compiler, which means you don't actually need to unload Intel compiler and load GCC compiler. You can simply do module load GCC. They will automatically unload Intel related packages, and then it's going to load the GCC, and at the same time it's going to replace OpenMPI packages with the GCC related OpenMPI versions. So when you change your module from Intel to GCC, now you can see the OpenMPI 2.1.1. It looks the same, but this OpenMPI for GCC actually is loaded. Sometimes certain type of job requires, A, B, C modules, and the other type of working situation requires, let's say, EDF modules. Then sometimes you may feel, typing every time module unload and load, those kind of things is such an annoying. So you may want to make some collection of modules for a certain type of job, and then you use another type of module collections for another type of job. So in our GRAM system, actually offers some options, module save options. So what it means, Graham allows you to create a collection of modules, and then you can load the desired modules and save it. And then you can restore it later on. So here is a short demonstration, you can see that. So here, simply, you can see that there's a module list is basically default. And then I want to change Intel compiler using GCC. So I loaded GCC. It will automatically replace Intel compiler and OpenMPI. If I check it out one more time, you can definitely see number 5 and number 6 that's related with the GCC. So I'll save this module list as my GCC module list, which means all the collections of modules are actually saved into my GCC. And then I can sometimes check it out what actually in our module list by using module describe. So once again, let me go back to Intel compiler. If I check it out one more time, now you can see that number 8, 7, and 8 is related with the Intel compiler. Now, if I want to go back to GCC modules, I just check it out what actually modules in my module list, and then I do module restore by GCC and then you can definitely see the module actually changed automatically. So this is very convenient tool because for me, I sometimes need to compile some code using GCC. I need to compile another package with Intel compiler. And sometimes I need to refer to different library and different packages as well. So it's really good idea to make some collection of modules for certain type of job and make another list for the other type of job. It's very convenient. There are something you better to know for modules. Only one version loaded at a time. So even though GCC has multiple versions available, but you should load only one version. And sometimes you have to, you want to load two different modules from same family, which means family means GCC or some compilers, those kind of big category. So only one module in the same family loaded at a time. So if you load GCC, you cannot load Intel compiler because they are same family of compiler. It's the same thing for the MPI modules too. You may want to load OpenMPI, but sometimes you want to use MVA pitch 2. At the time, you have to switch that. You cannot load both of modules together. And as I showed you, there is automatic replacement of modules with the dependencies as well. So that's a little bit different point from Sharcnet legacy systems. And also there are permanent or sticky modules which cannot be unloaded from your module list. Okay, now let's move to our scheduler, name of SLURM. What is the scheduler? If you used to a single box Linux machine or Macintosh machines, you may not familiar with scheduler. SLURM, the scheduler in Graham, is a resource manager because we have large scale hardware resources with multiple hardware nodes as well. So we need to control how to handle to submit the jobs to the individual node and how to use the memories, how to use the storages together. So SLURM, the scheduler in Graham, is a resource manager and job scheduler designed to do such that those kind of jobs. It is originally created by Livermore Computing Center, and then now most of supercomputers actually using SLURM system. Here is a brief schematic diagram. So left side is your side. You're actually at the client PC or laptop. You try to connect to graham.computecanada.ca using SSH connection. Compute Canada systems or all Sharcnet systems only allowed SSH connections. So if you're using Windows systems, you need to download PuTTY or Blueba Xterm, those kind of SSH client software in your PC to connect our systems. If you're using Linux or Mac, you can simply open the terminal and type SSH and make some connection to our login mode server. Once you log on to graham.computecanada.ca, that's basically login node. So login node is not the machine you can run your job on it because it only handles all the login activities, which means loading the module or simple compilation or checking jobs and submitting jobs, those kind of jobs. So login node shared by many users. Therefore, it is not recommended to run any job interactively at login node. Once you do module load compilation and making some job script, And then you're going to submit your job to SLURM system. Once you submit your job, the job actually goes to the SLURM system or SLURM software, and SLURM will control what is the most effective and efficient way to run your job, considering the existing jobs running on the computing node. So computing node will be controlled by this SLURM system. So SLURM will consider what is your requested runtime, what is the requested number of cores or CPUs, and what is the requested memory, and what is the kind of option of writings. And then SLURM will apply very complicated formula to allocate your job one of the computing node. And then your job will be run on the computing node and make some output such as Scratch or project or sometimes home directory. So SLURM, that scheduler, you should know how to handle those kind of system. So SLURM system will provide you many useful information by checking out. There are millions of options for SIM4 and many different commands. So please check it out using our wiki pages or Google and Compute Canada, SLURM, running job, wiki, those kind of commands. And as you see here, SIM4 is very basic command you can try. So by default, SIM4 lists the partitions that are available. This is a little bit difficult word, so let me just hold up. A partition is set of compute node. So SIM4 will give you the typically, all the partition information, what is the status, how many nodes actually grouped by, and those kind of information actually available. Sometimes people want to use some options using -n or -l together, or sometimes many different options. You can definitely see the multiple nodes available and some system information available as well. And here is SQ. SQ is another way to check up your job status or something like that. But I'm going to explain this one using the demonstration later on. So first thing is you have to know how to check the queue or how to check the job. Some people may wonder what is queue. Let me go back a couple of slides back. So queue means basically when you submit your job here, when you submit your job, there are just some pipelines actually to feed the job to the computing node. So there could be serial job queue, there could be MPI job queue, there could be thread job queue, and those kind of way. So when you specify your job is parallel job using MPI, then once your job is submitted, SLURM will put your job into the MPI queue, which is waiting line to be allocated on the system. So sometimes you need to check which queue is available right now, and sometimes you have to make sure what's your job type. Is it serial or parallel or threaded, or sometimes a GPU, and you have to put appropriate tag or appropriate queue information in your SBatch file, which is a job submission script, and so that the scheduler will appropriately allocate your job to the proper pipelines. Otherwise, for example, even though your job is parallel, if you assign the serial job tag or serial job queue, then once the scheduler just assign your job into the serial queue, that means your job must use a single CPU. Therefore, your parallel job cannot run properly. As I mentioned, SLURM, actually resource request consists in the number of CPUs, computing expected duration, amounts of memory, and disk size, and job steps describe tasks that must be done, software that must be run. A shorter time job or shorter runtime job will have a more scheduling opportunity than otherwise identical longer job, because it's easier to allocate those kind of jobs. So I'm going to show you a typical job submission procedure, and I'm going to show you how to use SQ or SINFO later on using demonstration. But generally speaking, the typical way of creating a job is write a submission script, job submission script, and a submission script is a shell script. I'm going to show you what it is, and bash script. And then we're going to submit it using the S-batch. That's the command to submit your job. And then SLURM will accept your job request, and then SLURM will allocate your job appropriately. So here are some steps. This is a typical job submission script for serial job. So serial job means you want to use single CPU. Couple of things you need to make sure here is I defined shop S-batch. This is kind of directive or some information for the scheduler. So you indicated I want to use 1024 megabyte memory. And then I set the name of job as a hello. And I set the output format as a SLURM, and %X is a job name, and %J, that's job ID, because when the SLURM allocate each job to the computing node, the SLURM will tag individual job ID on each job submission. So individual job submission you made will have a unique ID. We call it as a job ID. And then when you write down %J, that refers to that number. So individual job submission will have slightly different numbers. And then I allocated 2 minutes for this job. And the last line is kind of important because in our system, we have to make sure who actually run certain job, and also sometimes we tracking all the usages of CPU. So we need to know who actually are running this job. Therefore, you have to specify your ID. That's a slightly different name from your login ID. You can check it out by typing ID in your terminal or login node. And then the very last line is an execution line. So echo hello world. This is my job submission. So here's some demonstration I made. So as you see here, I already made some job underscore s.sh file, and then it is exactly the same thing I showed you before. And then using S-batch job. So S-batch is a command sending your job submission script to the SLURM system. So S-batch is the command to send the job submission script to the SLURM system. So I sent it out. When I sent it out, the SLURM will reply back to you with unique ID, that's a job ID. So we have very long digits for the job ID. And then we'll see the results soon. So by checking the result, as you see at the end of the list, SLURM, hello, job ID, and out. That's kind of output of this job. So if I check it out, it must have hello world. Yes, it is. And then I can check some information about the job, which is completed recently, by typing SACCT -J job ID and some format. You don't need to worry about this format right now, but this is typical, command I'm using to check out the job status or for the completed jobs. As you see here, simply name of hello for the job actually run pretty well with with the memories and everything. You can see that. Since the job actually completed, when I check it out my user ID with SQ, so SQ minus U Isaac, it doesn't show me any job because it's already done. So let me go back slightly. SACCT is used to report job or job step accounting information about active or completed job. SBatch is command actually to send your job submission script. Scancel, I'm going to show you soon. Scancel is used to cancel a pending or running job or job step. So we're going to use scancel to cancel the job uh, in a minute. And control is under administrative tools. I don't want to cover it right now, but there is some more information you need sometimes. You can use control. Here's another demonstration. I intentionally put one line more here, sleep 3000, which means when I submit this job, and if the job actually run, it's going to make some echo hello world, and it's going to wait for 3000 seconds. So which means if I submit this job, it will take some time to be completed, right? So I want to use that moment to cancel the job. That's why I intentionally put sleep 3000. It's not a common activity, so don't do this way. But this is only for the purpose of using scancel. So if I run a job, SBatch job script name, I'll get the job ID back from the scheduler. And then if I check my ID in SQ, you can definitely see my job actually running right now. Therefore, I'm going to cancel using scancel with the job ID. That's a very important thing. You should know what's your job ID to cancel it. And if I check it, my history using the S account, you can definitely see the job ID with, related with that job actually canceled. So 11320299 actually canceled. And then if you check the output with the same job ID, it will show you there's some cancellation happens. So you can see what I'm trying to deliver right now. You can cancel your job. You can check the status. You can see what was the result when you canceled the job. Okay, now let's talk about MPI job or some parallel job. So this is example of submitting parallel job. Here, only difference from the serial job is I defined number of a CPU. So I want to use 4 cores, and memory allocation should be a little bit different from serial job because we need to specify how much memory you want to allocate per CPU or per core. So I used a slightly different command for the memory, but you can always refer to this kind of details to our wiki pages. And I named the job as MPI hello, and same format for the output and time and ID. And lastly, I used srun dot slash MPI underscore hello. So this is the executable file in that directory. So I made a small demonstration here, so we're going to see that. So this is a simple MPI hello.c file, and then I want to run this one using MPI script, job submission script. So first, I'm going to compile it using MPI CC. This is a typical activity to compile it. So I'm checking the executable file, which made by MPI CC. And then once again, I'm showing the MPI job submission script. And then I submit the job as batch job underscore p.sh. and I'll get the job ID, and checking my account in the queue, you can definitely see it's running. Status is running. And then after a certain time, if I check the result, the same job ID log file or output file actually generated. So I'm checking out the output file. You can definitely see it runs perfect. Like I used 4 CPUs, and then each code or each CPU actually replied back to me. So this is good. And SLURM also has a very fantastic uh, feature of interactive running, which means if I'm a developer of certain code, sometimes you have to check if your code runs pretty well before you actually submitting the job for a long time run. Therefore, SLURM suggests you to use interactive running mode. So interactive running mode is kind of making virtual allocation for your working environment only. So interactive jobs are also supported in this kind of situation. So as I described here, data exploration at the command line, interactive console tools like R or IPython, or sometimes you need to debug or compile. Those kind of things are also possible in these large scale systems. So you can start those kind of interactive session, we call it interactive session, on a computing node as SLOC or SALLOC. So here is a simple snapshot of what I did. So first line, SLOC or SALLOC, and I define the time, how much time I'm going to use that virtual environment, which is actually I define the 5 minutes, and then I ask 2 CPUs, and then for my account. So you have to specify what is your account information there too. And then your login mode slightly changed to the virtual interactive mode. So you can definitely see what happened here in your prompt lines. Actually, it was login node, and now you're in one of the Graham node. So by allocating those kind of CPUs, and then you're in your machine, basically, not the Sharcnet machine or not the Compute Canada machine. So you can exercise whatever you want to do as interactive running. So here, instead of using SBatch to submit your job, you simply do the MPI run minus MP2 and then MPI hello, which means this is a typical way when you run your parallel job in your single node machine. So sometimes you want to run your job without submitting any job to the scheduler, just simply / your executable file. It's the same thing. So this interactive mode or interactive um, session is quite useful for the code developer or data exploration jobs. Once your job is done, all you need to do is simply exit, or you can just leave it out, but it's not a good idea because it will use your time. So please exit it, and then Compute Canada system will think about this whole session as allocation. So you have a job allocation like this, which means this allocation means interactive session. So this is very useful. So many people may wonder how to minimize my waiting time. To be honest, Graham system mostly occupied by resource allocation program. So 80% or 70-something percent mostly occupied by dedicated resource allocated programming jobs. Therefore, it's sometimes very competitive to run your job. So there could be some tips very useful for you. And first, the tip I can give you is specify the job time, slightly over than you expected. We recognize so many users just allocating the time, whichever large, like 7 days, 10 days, 20 days. But the longer time you set, there's the less chance you can run your job quickly. And memory-wise, it's another one. Memory is very important kind of part of job sometimes. So as I mentioned, each Graham node most likely have 128 gigabyte. So if you want to use like more than 128 gigabyte memory, which means we have a very limited number of physical nodes for that. Therefore, you have to wait a long time. Secondly, some of users allocating 128 gigabytes as a full, which means you believe each node has 128 gigabyte. Therefore, if I ask 128 gigabyte, it's kind of fitable to the single computing node. Actually, that's wrong because each node requires a couple of gigabytes to run their operating system and daemons, all the things. Therefore, even though physically each node has 128 gigabytes of memory, but it's not a good idea to assign 128 gigabytes to a certain node. So it will automatically move on to the 512 gigabyte memory machines. So it gets longer time to run. So please understand the real situation. So if I were you, if I want to use like 100 gigabyte memory, that's fine to run it. But if you targeted more than 128 gigabytes, you have to think about to use larger scale memory node. And there are many different constraints as well. Whole node only. Sometimes you want to use single node fully. So which means we have to, scheduler has to wait until certain node is evacuated, and then SLURM can accommodate your job into the whole node, right? It's really takes a long time. And there are many different, multiple factors to, resolve those kind of constraints. So you have to be careful. And do not package what is essentially a bunch of serial jobs into parallel jobs. So it is much faster to schedule many independent serial jobs than a single parallel job using the same number of CPU cores. Let me briefly touch the file management as well. As I mentioned before, we do have home directory, scratch directory, project directory. I'm sure you guys already went through our new user seminar. And the new user seminar, we covered some of the information about it. Most important part is scratch directory is not backed up or not metered for your backup. So you have to keep your important files in our home directory or project directory. One thing I want to say here is Nearline tape storage. We do have 5 terabyte tape storage. So when you need to kind of store your data for a long time, but you know you're not going to access to those kind of data quite often, then it's really good idea to, we say, archive the data into the tape material, because it doesn't consume your disk quota. Simply by putting your files into your home directory under Nearline and project directory, then system automatically back up those kind of data into our tape material, and then we're going to store them. So this kind of Nearline archiving is a very useful tools. Please be aware of that. And for the best practices, most important part is do not make very small, tiny scale or size files as many as possible. Do not make it. So you better make a big chunk. It's not too big though. Big size of reasonable size of file than the many small size of files. So that's very important. So here I want to suggest you is if you don't know how to use a tar, that's a command to group the files and compress the files. You better know how to use that. So tar file or tar command bundle a bunch of files and directories together and generate a single file. So we call that as archive file or tar file. And then later on, you need to compress them. So I'm going to show you my demonstration. You can definitely see there is a dramatic changes in the size of the volume. So here's a simple demonstration. let's say here's a directory name of Isaac has 4 files, MPI hello to MPI hello binary files. If I want to group those kind of 4 files, or I want to hook up all files into the one file, then I made a tar CVF, tar CVF, and target name, so isaac1.tar, and the target directory. That means isaac1.tar file actually holding right now those 4 files. I do have those 2 files now. And then you can sometimes generate tar file as a compressed file directly. So as you see here, isaac2 tar gz is a compressed file, which is compressed file of those kind of tar file. So as you see, the first isaac1 tar has 133, 120 byte size, but the compressed file isaac2.tar.gz has way less kind of volume size. And then sometimes you want to see what's the list of the tar file inside without extracting the file. So using T options, you can definitely see some file list of the tar file, and sometimes possible to see the file list of compressed tar file as well. And then I'll show you how to extract the tar file. So I made a sample directory and copy the tar file to that directory and extract it. So I don't have anything in test1 directory, so I'm going to copy the tar file to this directory. And then you use simply XVF. X is extract, C is a compress. So you can see that here I can extract all the files. When you have compressed file, we can do same thing by copying the compressed tar file to this directory. We simply use Z option here. You can definitely see there are a list of files, and then we got the files. Once again, Nearline is a very, very useful tool, so please use that. It's not going to cost you your disk quota, because if you hitting the disk quota, you will have some limitation in activities on Graham system, like submitting a job. Okay, thank you.